Optimization Problem. So we were taking the bracketing and open methods. So we were talking about the cold section, quadratic methods, and the Newton methods. So we are saying that it's the bracketing methods of golden section. It has two initial value of x lower and the value of x upper. Quadratic method, it has three initial values of x0, x1, and x2. Newton methods, it has just only single initial value of xi. Okay. So this is we call is unconstrained optimization because we are trying to find the highest value, which is going to be maximize the function or minimize the function. There's no restrictions. You can iterate many times, but there is no rule for you to stop. Maybe during the question we are going to ask to stop when the error is reached a level or one value, let's say 5% or 4% or 1%, whatever. But unconstrained optimization is most of the time is we are trying to find the maximum value, which is the global maximum or the global minimum. Today, it's our solving for optimization a little bit different because we are going to deal with constraint optimization problem. So that means we are not freely need to find the maximum or the minimum value of a function. There will be some limitations in there. So this is what we call here is the multi-dimension constraint optimization. And also it's called as a linear programming. So linear programming, it's considered as an optimization approach. It deals with meeting a desired objective, such as maximizing a profit or minimizing a cost. This is the most important here in a presence of constraint, such as a limited resources. What does it mean here for linear programming? It's dealing with you. It's like you are a businessman or you are a businesswoman and you are trying to make your business. Okay, so if you are a businessman, your objective most of the time is to increase your profit, or you want to maximize your profit. You want a lot of money to be a profit for you. And at the same time, as a businessman, you want to minimize your cost. You don't want to pay more. But actually, you are not, as a businessman, you can just simply maximize your profit by controlling the price. You need to get, or you need to bear in mind that there is some limitations that you are going to face. Let me give you an example here. Okay, let's say that you are a businessman and you are in a business of Jual Nasi Lemak. So this is a concourse of Nasi Lemak. Okay, so the idea of a businessman for optimization, of course, you need to maximize your profit and minimize your cost. So let's say that I'm going to tell you that you already established your business, then suddenly you decide that you are going to sell your nasi lemak with this price. Is it okay to jual nasi lemak with the 15 ringgit?
No.
No, too expensive.
Okay, too expensive. Why you are saying that it's too expensive? Because you are controlled by the price market. There is a people they are selling the nasi lemak. Normally you can get the nasi lemak with the price of 2 ringgit, 3 ringgit. Also you can find maximum, maybe you can find 5 or 7. So this is the maximum price. So now you are, as a businessman, now you already said that I want to maximize my profit with the 15 ringgit. But actually, I cannot maximize it with the 15 ringgit. Why? Because I am limited to the market price. So that means I am not freely to maximize my profit. That's why we are saying here, we are dealing with constraint optimization problem. So that means I am not freely to maximize something or minimize it. Okay. Another thing is also, you can see it in here. If you want to maximize your profit, let's say that you understand the market So you are saying that you are going to jual your nasi lemak with the price of 5 ringgit. So this is good. But again, you are as a businessman, now you want to maximize your profit. So let's talk about the time. If you start your business at 7 a.m. morning, to 10 a.m., or you want to start your business at 6 a.m. till 8 p.m. Which one is going to be maximize your profit? The first time or the second time? The first one. This is AM. This is AM. The second one, this is PM. Okay. Here you are going to, of course, here you are going to maximize your profits. This is the correct choice. But for you as a businessman, let's say that you are the one working to do the national map. Are you really able to work from 6 a.m. to 8 p.m. by yourself? Maybe you can, maybe you cannot. But this is something that you are constrained about the time. Maybe it's you can work from 6 actually. You can work from 6 a.m. maybe maximum, because you are still human. You are tired, so maybe you are going to stop at 3 p.m. So you can see from here that it's the time also considered is a constraint. You are not just only freely to use any time, because you are like a human, you need to rest sometimes. So this is some restrictions. There's also another things, maybe store. If you are having, if you are starting your business and you are having what you call it a shop, that shop in a mall, and the space for your shop is really huge, so you can use the store, the size of storing. So you can prepare nasi lemak in a big portions of quantity, and you can store it in a large space. So this is also going to be maximize your profit. But let's say that you don't have that ability to rent a shop, so you just only rent a small crate or a small stroller. So you are selling your nasi lemak. So that's mean when you are having a small stroller, you cannot maximize your profit same like you are having a shop or a kadai. So that's mean the space also, or the storage also, consider it's a limitation for you. So this is what we mean here about I am dealing with constraint optimization problem. So now, is it clear what does it mean that you are having an objective function to maximize the profit and minimize the cost in a presence of constraint? Such an process. Any questions about this part? Is it clear?
Yes, sir.
Okay. So the mathematical function is going to be representing both. That's mean in our case here for constraint optimization problem, we are going to have two major parts. The first part you're going to have is the objective function, which is the objective function is to be maximize the profit or minimize the cost. And the second equations is going to be the constraints, which is, let's say, it's the time, the storage, the cost. So this is what we have. The name of the methods we are going to use to help us to solve the linear programming or the constraint optimization, we call it's the simplex method. So this is the only method that we are going to use for this chapter to solve for the constraint optimization. Okay, so the standard form of linear programming problem or constraint problem, it's the basic linear programming problem. It consists of two major parts: the objective function and the sets of the constraints. So what you need to do during the final exam to start to solve for the linear programming, the first step, you need to convert the problem into the standard form if it's not already in the standard form. Why we are saying this? because some of the questions at the final, it's coming in a form of a story of a factory or a story of a company. They are trying to produce a product. So let's say product A and B, and the company or the factory, they are trying to maximize their profits with a certain amount. And they are going to tell you that it's the factory, it's the manpower over there. They are working, let's say, 4 days in a week. And the storage to store product A, it's different from product B, and they are going to give you the values. So they are going to give you in a form of paragraph. So by yourself, you need to extract, you need to convert it into the standard form. The standard form, that means you need to extract the objective function to be maximized or minimized. And also you need to find the set of the constraints. I think if you have the previous semester's final examination, you are going to see how the type of the question is coming from this part. So you can get used to. So this is the methods we are going to use. This methods, it's assumed that is the optimal solution will be an extreme point. So that's mean the solutions that you're going to find, this is the extreme points that is going to give you the maximize or minimizing the objective function. So while we are solving, you need to discern or you need to check whether during the problem solutions the extreme points occur or not. Okay, so if it's happened that you already found the extreme points, you are going to stop and you are going to conclude your solutions to say that this is the value that it's maximizing my objective function, and you are saying what those values are. So to do this, we are going to be introduced something we call is constraint equation will be reformulated to as equality by introducing a slack variables. This is, I'm going to explain it during the example to solve. Okay, so now the first things that we are going to take today is the standard maximization problem. So the maximization problem is the standard for if the objective function is to be expressed in this form, and objective function is to be maximized because we are talking about maximization problem. And also you are going to have a set of constraints, like 1, 2 constraint, 3 constraints, or n number of constraints. So what's the characteristics of this maximization problem? So you can check it from here. The characteristic of standard maximization problem is the objective function is to be maximized. So in my case in here, yes, this is my objective function and I need to maximize. So this is true. All the variables are non-negative for the x's, and we are looking here. All the variables here for all the x's here, it's non-negative. All of them is positive. So this is true. Each linear constraints in a form of less than equal to a non-negative constant value of b. When you check your constraint, you need to get this sign in here, which is less or equal to non-negative constant value of b. So this is when you see these things in here, so that's mean you know that this is the standard maximization problem. We are going to do this one with our example, and I will solve this example with you one by one. The second example, you are going to do it by yourself. Then you are going to check your answer. So when we are looking at this simplex methods of standard maximization problem, this is the example. We need to maximize this objective function, which is subjected to these two constraints. This is your first constraint, and this is your second constraint. So when we are looking at the characteristic of this maximization problem, the objective function is to be maximized, true. All the values of the x's is non-negative, yes, it's true. And when we are looking at the constraint, they are in a form of less or equal to non-negative value. So this means true. So this is the three properties of the maximization problem. So this means we are having the standard form of maximization problem. So now, how to solve. The first thing we need to do here to solve this maximization problem, we need to convert the constraints into the form of equality. So this means we need to get rid of this less or equal sign. So we need to make it into a form of equality. So to make this one in equality, we need to introduce something we call it is the slack variable. So what does it mean here? So now let's make this one in a form of equality of equation. So the objective function to be maximized, p is equal to 10x plus 12y. We are going to convert it to p minus 10x minus 12y will be equal to 0. For the constraints, we are going to introduce the slack variables. So this means this one to get rid of this, we are going to write it x plus 2y plus slack variable 1, s1. So this sign will be gone, will be to the equality 12. The second constraint will be equal to 3x plus 2y plus s2 is equal to 24. So this is your first step of the solution, converted into the standard form. So this is what we have it here. Okay, so next, what you are going to do with all the values in here and the coefficients, you are going to create a table. Make me a favor here. This one is not integration. I don't know why they are writing this one. This is intercept. This is intercept. It's not integration. Intercept. We are going to create all the variables and the coefficients, and we are going to put the values in form of this table. But there is one condition that we are going to do here when we are creating the table. Make sure that is the first row. The first row is having the objective function, having the value of the objective function. So one condition here is the first row supposed to have the values from the objective function. The second row or the third row or the fourth row, it can go for the constraint. So now let's see how we are going to put the values. Okay, so I have a variable p, I have x, I have y. So p, x, and y. I have s1 and s2, so s1 and s2. So remember that we are saying is the first row is the objective function, so it's p. And here you are going to put the slack variables of the constraint, s1 and s2. Now we are start to put the values. So now first we look at the objective function. For the objective function, it has p, so it's equal to 1. X is equal to -10. And y is equal to -12. Does the objective function has any slack variables? No. So it's equal to 0. It's equal to 0. What's the solution of the objective function? It's equal to 0. Okay. Now we start with the first constraint. Does it have p? No. So it's 0. X is equal to 1. Y is equal to 2. S1, yes, is equal to 1. Does it have S2? No, it's equal to 0. What's the solution? It's equal to 12. And now we go for the second constraint. Does it have P? No, so it's 0. X is equal to 3. Y is equal to. Does it have S1? No, so it's 0. Does it have S2? Yes, is equal to 1. And the solution for it is equal to 24. Okay, clear to this step? Any question?
No, sir.
Okay, so now what we need to do, okay, so we already have done all this. We put all the values in the table here. Okay, so what I need to find here, remember I told you in the group that we are going to do something for the naive Gauss Jordan. So to do the naive Gauss Jordan, remember that I need to get the pivot element is equal to 1 and the rest is equal to 0, right? So now to find the pivot element, I need to find the pivot column, then the pivot row. That's why we are saying this one is the intercept. It's not integration. So I need to find a column and I need to find the row. So to see where is the column and the row, they are intersecting. Something like this. So this column and this row, they are intersecting at this value. So I want to locate this value. So how I'm going to do that? Okay. The first thing in here, you are going to look at the objective function. You are going to look at the first row. And they are going to look at the most highest negative value. So in my case in here, it's the highest negative value that I have here. It's for column Y. It's equal to negative 12. So Y is going to be my pivot column. Okay, remember that. I am looking at the first row, which is my first row is my objective function. And I'm looking for the highest negative value. So in my case in here, my pivot column is Y. Okay. So what's next, or what you're going to do now? I found the column. Now I want to find the row. So now I already found the column, which is Y. So I want to find which row is going to be intersecting me. Is it S1 or S2? How to find the intersecting row? I need to make some calculations. Intercept over the solution. Sorry, the solution over the column Y. So this value I'm going to divide over negative 12. 12 I'm going to divide over 2. 24 I'm going to divide over 2. So I'm going to get the answer of 6 and 12. Clear? Okay. Any question?
So can you please repeat it again?
From which step?
The integration equal to solution divided by y.
This is not integration. This is intercept.
Oh, yeah, I mean intercept. So.
Okay. Okay. I already found the column Y, which is my pivot column. So now I need to find the intercept. So the intercept is equal to the solution column over the pivot column. So in my case in here, 0 over negative 12, 0. 12 over 2, 6. 24 over 2. The answer is 12. Okay?
Okay.
Okay. So now, when I get the intercept column, so now I can say which row it's considered is my pivot row. So now I already have the column. So now with the intercept column, now I can tell which row is considered my pivot row. So I can find the intercept here. Okay. So how I choose the intercept based on those two values. So what value I should choose in here? So at the intercept column, you are going to choose the smallest positive value. So in my case in here, 6 is my smallest positive value. So this means my intercept row is this one, or my pivot row is S1. So to choose the pivot row, you choose the smallest positive value at the intercept. So in my case in here is 6. So this is become my pivot row. So when I already found my pivot row, don't forget this step. You need to delete S1. You have to delete it and rename it as Y. So in my case in here, I already found my pivot row. So this one will become as Y. Okay. So now this is the time for the Gauss-Jordan. I need to get, this is considered my pivot element. I need to make it is equal to 1. And this value, I need to make it to be equal to 0. And this value need to be equal to 0. And of course, when I'm doing this one, I'm not doing it with the column. I'm doing it with the whole matrix here. Doing it with the whole matrix. Okay. So once you're done with the Gauss-Jordan with the matrix, your matrix will be totally changed to be like this. Your matrix new is going to be like this. So now this is the time when we said at the slides, at the simplex methods, this approach must discern whether during the problem solution an extreme points occur or not. So now this is the point. This is the point now to check, did we achieve the answer or not? Okay. In our case in here, how you are going to know that you already achieved the answer or not? You need to look at the first row. So if there is no negative value or all the values is equal to 0, so this means you already achieved the answer. If still there is a negative value, you need to repeat the same steps back again. So in my case in here, I still have x, it's -4. So that means I didn't find the solution yet. I need to iterate one more time. So is it clear? So this is the whole methods. Is it clear? Okay, so now
Yes, sir.
let's repeat the same steps again because I'm still having -4 in here. So what I need to do, I will choose X as my pivot column because this is considered is my highest negative value. Then I will divide 27 over -4 to get the intercept, and 6 over 0.5 to get the intercept here, and 12 over 2 to get the intercept in here. Then I will choose the smallest positive value. So in my case in here, X is my pivot column. And when I get the intercept, I divide 72 over -4, so it's -18. 6 over 0.5 is 12. 12 over 2 is 6. So I want to now to choose my pivot row. My pivot row will be equal to S2 because this is the smallest positive number. So don't forget, S2 will be gone and will be replaced by the header. So it's going to be equal to X. Then I will solve again this one with the naive Gauss-Jordan. So I want to make this value is equal to 1 and the rest here is equal to zeros. Okay. Now you already found the solution. You need to check back again. Look at the first row. There is no negative values, right? So this means you already find the solution. When you find the solution, don't forget to write this box in here. This box is 2 marks. In the final exam, we are giving you 2 marks only, just only to say this. So you need to translate what does this table mean. So you are looking at the solution column. So what you are going to say, your objective function is going to be maximized by the value of 96. So you're going to maximize the P with the value of 96. When X is equal to 6, when X is equal to 6, and Y is equal to 3. So don't forget, you need to explain what does this table mean. because you are going to have 2 marks for that. So you are going to maximize your function with the value of 96 when y is equal to 3, when x is equal to 6. Okay, so that's all for the optimization problem. Do you have any question? Okay, I will go with you because now I know is the simplex methods by itself is not that difficult. The only difficult parts now you are thinking how you are going to do the naive Gauss Jordan. So I will go with you with this example one by one. If you want to follow up with me so you can make it, because the next example you are going to do it by yourself from A to Z. Okay, so now let's see how. This is your this is the example. T is equal to 10x plus 12y, and this is your constraint. You need to convert it to a linear programming standard form. So your objective function will be equal to p minus 10x minus 12y. You need to write this one, by the way, because when you write those things in exam, you are getting 1 mark, 1 mark, 1. So that means if you have 3 equations in here, you're having 3 marks. If you didn't write these things in here, 3 marks is gone. So p minus 10x minus 12y is equal to 0. This is 1 mark. Then you are going to introduce the slack variable. X plus 2y plus s1 is equal to 12. This is 1 mark. 3x plus 2y plus s2 is equal to 24. You are going to put the values in the form of this table. Okay, so the first thing, you need to find your pivot column. Your pivot column here is y, because it has the highest negative value. Okay, then you are going to divide the solution column over the pivot column to calculate the intercept. So in this case in here, you are going to divide the solution column over the pivot column to find the intercept. So 12 over 2, 6. 24 over 2, get the answer of 12. So now this is the time to select the pivot row. So this is my pivot row. So don't forget that it's y will replace s1. So y will replace s1. So now it's here. Y. Okay. So now since you found the pivot column and a pivot row, so now this is your pivot element. You need to make this element is equal to 1. So what you are going to do? How I can make this value is equal to 1? You need to divide over 2, right? 2 over 2 is equal to 1, right? But when you are going to do that, let me hide this first. When you are going to do this one, you are not just only dividing the pivot column. You need to divide the whole row. So that's mean 0 over 2, the answer is really equal to 0. 1 over 2, the answer will be equal to 0 0.5. 2 over 2, the answer will be equal to 1. 1 over 2, it's 0 0.5. 0 over 2, the answer it will be equal to 0. The solution 12 over 2, so the answer will be equal to 6. Okay, so now this is my pivot row. Remember, still we are on the pivot row. So now I want to make this value here is equal to 0. How I can make this value is equal to 0? So I need to make 12 minus 12, the answer will be equal to 0, right? 12 minus 12, the answer will be equal to 0. But I need to use with the help of my pivot row. So my pivot row here is row number 2. So if I say 12 times 1, the answer is equal to 12, right? Plus negative 12, the answer here will be equal to 0, right? If I say 12 times 0, 12 times 0 plus 1, so the answer will be equal to 1. If I say 12 times 0.4, so it's going to be 24. Sorry, 12 times 0.5, so it's going to be 24. 24 minus 10, so the answer here is going to be equal to negative 4. If I say 12 times 1 plus negative 12, so the answer will be 0. 12 times 1, this is my pivot row. 12 times 1, so it's going to be 12. And you're going to minus it from here, so the answer will be equal to, okay, what's the, I start to be confused also. Wait, let's start from scratch here. Okay, the rule is in here. Can you see this one clear? 12 times, okay, 12 times R1, R2, 12 times R2. That means you are going to get the 12s, you are going to times it with all these values. Let's make it here. It's equal to 12 times those values. Now, 1, 2, 3, 4, 5, 6, 9, 10, that's it. Okay, so now if I minus this row from this row, what I'm going to get? So 1 minus 0, it's equal to 0. Times that's it. Okay, so now we are making like this. 1 minus 0, so the answer here is equal to 1. Negative 10, you are going to get it with the minus of value in here, so you're getting the answer of, this is what's happening here. It's not negative 4. Okay, sorry, it's my mistake here. Yes, this is the values. Okay, so this is your pivot row. So you are making 12 times 0, 12 times 0 0.5, 12 times 1, 12 times 0 0.5, and 12 times 0, and 12 times 6. So this is the one. So now you are getting the value of 0, 6, 12, 6, 0, and 72. So now when you're making 1 minus 0, it's 1, and negative 10 minus the value of 6, so it's negative 4. Negative 12, this value, so the answer here will be equal to 0. S1 is 0, minus the value of 6 in here, so you're getting the value of 6. 0 minus 0, you are going to get the value of 0 here, and 0 minus 27, so you are going to get the value here of 72. Okay, you need to repeat the same, but for this row in here to make the answer here is equal to 0. So it's the value here, it's 2. So how I can get this value is equal to 0, I need to get negative 2. So if I say it is equal to negative 2 times my pivot row, so I will have those values. Okay, so now if these values minus those values, so what you're going to get? 0 minus 0, so the answer is 0. 3 minus with 1, so you are going to get the answer here is 2. And 2 with the minus of the plus the value of negative 2 here, so the answer will be equal to 0. And what you call it here, 0 minus the value here, so the answer here will be equal to 1. And 1 with the value here, you are going to get the value of 1. And 24, you are going to get the value of 12. Okay, so don't make this one as a negative. This one is 2. Okay, so now again, you already have found this solution. You need to check if your first row there is no negative value, so you need to repeat the same steps back again. So in my case in here, y is going to be my pivot column. Then I'm going to divide the solution over my pivot column. So it's 72 over negative 4, 6 over 0 0.5, 12 over 2. So I need to find the intercept. So when you find the intercept, you find that it's the smallest positive value. So in my case here is 6. So this is my pivot row. And don't forget that you need to replace S2 to be X. Okay, so I want to make this value here is equal to the value of 1. So I need to divide the whole row over 1. Over 2. So 0 over 2. So you get the answer of 0. 2 over 2, the answer here is equal to 1. 0 over 2, it's 0. Negative 1 over 2, so it's negative 0 0.5. And this is 1 over 2, it's 0 0.5. 12 over 2, you will get the answer of 6 in here. So now this is my pivot. This is my pivot row still, but this is the one I'm going to use it to eliminate these two values to be equal to 0. So to eliminate the first one to be equal to 0, I will times 4. It's equal to 4 times this row. Okay, so now 1 minus 0, it's 1. Negative 4 would going to be with the minus of this value here, so you are getting the value of 0, and 0 with the 0 in here. So the answer here will be 0. 6. You're going to minus it from this value, so its answer here is 4. And this one is 0, the minus of 2, and 72 with the minus of this. So you're getting the value of 96. Okay, it's a negative value. Okay, so now the the value of that we want to eliminate here, it's 0.5. So it's equal to 0.5. We need to times it with a pivot row. So 0 minus 0, it's 0 here. 0.5 minus 0.5. Now this one becomes a 0. Remember that this is my pivot column. And 1 minus 0, so the answer is still 1. 0.5, 0.5 with the negative of 0.25, so it's going to be 0.75. 0 with the 0.25, so it's negative 0.25. 6 minus 3, so you're going to get the answer here is equal to 3. Now you are looking at the first row. The first row, there is no negative value, you achieve the answer. So you need to say the answer of this function will be maximized by 96 when y is equal to 3 and x is equal to 6. Take these two values of 6 and 3 and you put it at the original equation here. So if you put 6 and 3 here, you will get the answer of 96. This is just only to confirm your answer. So that's all for the maximization problem. Okay, what I can give you, I will give you about, let's say, 15 minutes. I want you to solve. Try to get the same exact answer, 15 minutes. If you have any questions, please do ask. Then we go for the last minimization problem using the simplex methods, and we are done with this chapter. If you have any questions, please ask. But you need to try it by yourself. If you didn't try, you're not going to get anywhere. As you can see, even for me, I start to confuse about the Nave goes Jordan. So it's better to see the number in front of your eyes. So when you see the numbers in front of your eyes, then it's easy for you to understand what's going on here. Okay, so let me talk about the minimization problem. So the minimization problem is the standard for if the objective function to be minimized. So you can see this is the objective function. And also the same like the maximization problem, it has a constraint. The only difference in here that it's the sign here, it's greater than equal to a non-negative constant value. That's the only difference between maximization and minimization. Maximization, the sign was less than equal to a positive value of b. For minimization, it's greater than equal to non-constant value of b. So the characteristic in somehow is the same. So the objective function is to be minimized. All the variables is non-negative. The only difference here is I told you is they are using the signs of greater than equal. Okay, what's the good things about the minimization problem? That there is no specific way or there is no new method to solve. So the minimization problem to be solved, you need to convert it to be a maximization problem and solve it as I showed to you right now. So if the question is coming, asking you to get a minimization problem, so how is the way of solution? You need to convert it from minimization to maximization and solve it the same. So it means you are going to create a table. Then you are going to find the pivot column by finding the highest negative value. Then you are going to divide the solution over the pivot column to find the intercept. With the intercept, you are going to find the pivot row. So it's exactly the same like you are solving maximization problem. The only difference in here that how you are going to convert from minimization to be a maximization problem. Okay, so is it clear? Okay, so minimization problem, the way to solve it, you need to convert it to a standard maximization problem. So that's why we call the minimization problem, it's dual maximization problem. So now, how actually you are going to convert from minimization to be a maximization? This is the steps. It's really simple. But I'm going to show you the example, but you are going to solve the example by yourself one by one. Then you are going to compare your answer with my slides. Okay, so this is the standard minimization. Okay, so this is the example. The example is find the minimum of value of this function subjected to these three constraints: 60x plus 60y greater than equal. And when you are checking for the properties of this minimization problem, the objective function is to be minimized, yes. All the values of the x's is non-negative, yes. You can see it from here. And all the constraints on a form of greater than equal to non-negative value, it's true. So this is standard minimization problem. So to solve it using the simplex methods, you need to rearrange those values in a form of a matrix. But you need to make sure that here you are going to have the objective function is the last row. Make sure that you are making the objective function is the last row here. So let's see, you start with the constraint 60, 60, 300. So 60, 60, 300. Okay. Then 12, 6, 36. 12, 6, 36. 10, 30, and 90. 10, 30, and 90. Okay. And the last one, you are going to put the objective function 0.12 and 0.15. Okay. What you're going to do, you're going to transpose this matrix. You're going to rotate it 90 degrees. So the columns will become a row. So the columns will become a row. So this is going to be your first column. This is your second column. This is your third column. This is your first column. So your first column is 60, 60, 300. So now it's become like this. Your second column is 12, 6, 36. 12, 6, 36. And your third column is 10, 30, 90. And the solution will be equal to 12 and 15. Okay, that's it. This is how you transform from minimization to be maximization. So now this is considered is your maximization problem. Is it clear? Any question?
Yeah.
What is the question? Ask. It's what? Yes, because now this is going to be considered your new maximization problem. So your objective function is 300 plus 36 plus 90. This is your objective function now. And your constraint now is, your first constraint is 60U plus 12V plus 10W less than equal to 0.12. And your second constraint is 60U, 6V, and 30V is less or equal to 0.15. And remember that for minimization problem, this value is greater than equal. When you transform it now to be a maximization, supposed to be less than equal. So now like this one. So now this is now your new maximization problem. So this is what I want you to solve from A to Z. Okay, any question? Okay, so now put in your mind to transform or to convert minimization to maximization is 2 steps. Put the value from the question in a table and transpose it. You have to transpose. That's this is how to convert. And make sure that it's the last row is the objective function. Okay, so I will give you about half an hour. So I will back to you. What's the time now? It's 11:10, so maybe I will back to you about like 11:30 or 11:35. So I want you to solve it complete. Okay, anyone getting the same exact answer like this? Can you see my screen? Did you get the answer like this? Okay, never mind. So that's mean if the last one is wrong, that's mean your first iteration is perfect, correct? But now is the question is when you are going to have the final table, which is coming into this form, you already found the solution. As I told you that there will be 2 marks, these 2 marks to summarize what's the final answer. So I want someone to answer this. How you are going to summarize or what you're going to tell about these values. The previous optimization, we are saying here it's you are going to maximize the objective function to be maximized with the value of 96 when x is equal to 3 and y is equal to, when x is equal to 6 and y is equal to 3. In our case in here, what you're going to tell, what you're going to say. Yeah. The first row is the objective function z. Yes. Okay. So the first statement you said is correct, which is you are going to minimize. Because remember that we are talking here about a minimization problem. Even though we convert it into a maximization, but still you need to say that the objective function will be minimized by the value of 0.66. But which values they are going to actually, it's controlling the objective function, not this value, not this value. You are going to say it like this. The solution is the dual maximization problem or the minimization problem would be minimized by the value of 0.66, okay, when the value of x is equal to 3 and the value of y is equal to 2. So we are using these two values. So now this is the question that is going to show that you really understand what's going on here or not. Why I choose these two value, I didn't choose these two. Why I choose 3 and 2, I didn't choose these two values. Can someone tell?
Objective function.
Yeah, why I choose now? Previously for the maximization problem, I am using the column here. I'm using these three values, 96, 3, and 6. But for minimization, I am using 3 and 2. I'm using the row. I'm not using the column. Anyone? Yes, very perfect. Remember that at the beginning of solution of minimization problem, when we are converting into maximization problem, we transpose the table. So when you transpose the tables, rows become the row and columns become the row and the rows becomes the column. That's why at the last of your solution, what you need to say in here that this is your answer is you are going to be minimize the function with the value of 0.66 when x is equal to 3 and y is equal to. You want to confirm the answer, take the value of 3 and 2 and you put it back into the original equations, you are going to get the value of 0.66. Okay, thank you very much for that answer. Okay, I want to share something with you. If you go for the future, I created here a forum for the optimization. So I'm covering here the two topics of one dimension with the golden section and quadratic. If you open, you're going to find here some videos from YouTube. And also I'm giving you here the slides from the quadratic interpolations. So you can refer back to it anytime. And for today's class, multi-dimension constraint, I give you some videos for the maximization and minimization. And also I am sharing these slides, which is this PDF file. So you can find the examples and you can go through. So we are just stopping at minimization problem. This is some examples. Maybe you want to look at it. So you are going to find this one here on this link of the future. Okay, so that's all for the minimization chapter. Since we are saying that next Tuesday is Tuesday, so you are not going to have a class, but the lab session, I'm going to show you how to use Microsoft Excel to solve for the maximization and minimization problem. You are going to see it's really how to use Microsoft Excel to find the final answer. It's just only by using the solver from the Microsoft Excel. So if you have any question now, please ask. If not, so that's all for the class today. I will see you inshallah for the next week. You have any question?
No.
Okay, if you don't have any questions, so please write the attendance for today.